This is Bob Capetta, and this lesson is the analysis of three sets. So we're going to start with our universal set, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The universal set is the set of items that you're going to explore, you're going to examine. The set A will be 1, 2, 3, 4, 5, 6, 7, 8. The set B, 2, 4, 6, 8, 10, 12. And the set C will be 3, 6, 9, 12. So we can do some various things with these things. We've studied complements, intersections, and unions. And what I'm looking for here is the set A union B intersects C. Now, order of operations are important. So the parentheses here tell me that I should do B intersects C first. So what are the items that are common in both B and C? 2? No. 4? No. 6? 6 you can see is in B and C. 8, no. 10, no. 12, yes. So B intersects C gives us the items 6 and 12. A up here gives us 1, 2, 3, 4, 5, 6, 7, 8. Union tells us we're either in this first set or the second set or both. Well, let's see. 1 is in the second set, 2 is in the second set, 3 is in the second set, 4 is in the second set, 5 is in the second set, 6 is in both, 7 is in the second set, 8 is in the second set, 9 is missing, 10 is missing, 11 is missing, but 12 is in the first set. So the union includes all of those, 1, 2, 3, 4, 5, 6, 7, 8, together with 12. And the ones that were missing were, of course, 9, 10, and 11. So we've constructed the set of items for A union, quantity B intersects C. So that's the sort of process that we're going to use to identify elements in sets like this. So let's stick with the same collection of sets, our universal set, our set A, our set B, and our set C. And this time I want to find A union B intersect A union C. So let's start with A union B. What are the items that are either in A or B or both? Well, we have 1, 2, 3, 4, 5, 6, 7, 8. So 2 is included in both, 4 in both, 6 in both, 8 in both. So we have all of these, plus we have 10 and we have 12. So 1, 2, 3, 4, 5, 6, 7, 8, 10, and 12 will be in the union. And several of them are in both. But right now this is what we have for our union. How about A union C? Well, 3 is in both sets, 6 is in both sets, but what's in one or the other or both? 1, 2, 3, 4, 5, 6, 7, 8. What am I missing? 9 and 12. So A union C, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 12. And we're going to finish this by taking the intersection of these two sets. So let's go item for item to see who is in both sets. Remember, to be in the intersection, you must be in both sets simultaneously. 1, yes. 2, yes. 3, yes. 4, yes. 5, yes. 6, yes. 7, yes. 8, yes. 10, no. 9, no. 11 is missing in both. 12, yes. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, followed by 12. That's the intersection of these two sets. So you're looking at two sets at a time, A union B, A union C. Find the items that are common to both. And let's extend this example one more time. There's our universal sets, same sets A, B, and C. This time I want to find A intersect B union C complement. Now this complement is just on the C. If I wanted the complement of all together B union C, I would need parentheses. So this complement is just on the C. That means the complement of C. What is in C? 3, 6, 9, and 12. So throw 3, 6, 9, and 12 out from the universal set. What's that going to give you? 1, 2, 4, 5, 7, 8, 10, 11. That is C complement. 1, 2, 4, 5, 7, 8, 10, 11. That's C complement. Now I need stuff that's in C complement or in B. I'm going to do B union C complement next. What is in B or C? Well, let's go. 1, yes, is in C complement. 2, yes, is in both. 3 is in neither, so we're skipping 3. 4 is in both. 5 is in C complement. 6 is in B. 7 is in C complement, 8 is in B, 9 is in neither, skip 9, 10 is here in B, 11 is in C complement, 12 is in B. So we have an awful lot in there. What did I skip? 1, 2, I skipped 3 and 9, and I believe that's it. So that is our set B union C complement, either in B or not in C. And in A. So now we need to see, this is B union C complement, and there is A. So which items are in both sets simultaneously? Let's look. 1 and 1, yes. 2 and 2, yes. 4 and 4, yes, not 3. 5 and 5, yes. 6 and 6, yes. 7 and 7, yes. 8 and 8, yes. Not 10, not 11, not 12. So what do we have then for the intersection of this set A and this set B union C complement? Might be, again, simpler to start from this one. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, skip 3, 4, 5, 6, 7, 8. There you go. 1, 2, skip 3, 4, 5, 6, 7, 8. That is that set. So we need to be comfortable looking at unions, intersections, complements, putting them together for multiple sets, for 3 sets in this circumstance. Okay, next we want to construct a Venn diagram for A intersect B. Notice the order of operations. That's what's going to be done first, union C. So we're going to number all of our regions. We have our universal set with the rectangle, regions A, B, and C, sets A, B, and C. Regions 1, 2, 3, 4, 5, 6, 7, and 8. So that's the standard numbering I'm going to use. Now, A consists of regions 1, 2, 4, and 5. Let's take a look. A consists of regions 1, 2, 4, and 5. So you'll notice I put yeses in 1, 2, 4, and 5 for set A. B has which regions? 2, 3, 5, 6. B, 2 is a yes, 3 is a yes, 5 is a yes, 6 is a yes. C, which regions? 4, 5, 6, 7. C, 4, 5, 6, 7. So I've identified each of the 8 regions, and I've put yeses if they're in the set, nos if they are not in the set. Now the first thing I need is A intersect B, A intersect B. A and B at the same time. If A is a yes and B is a no, intersect is a no. A is yes, B is yes, so A intersect B would be yes. No yes is a no. Yes no is a no. Yes yes for intersect in both sets at the same time. Yes yes would also be a yes. No yes would be a no over here. No no is a no. No no is a no. So for A intersect B in both at the same time, I just have this yes yes region 2 and this yes yes region 5. Everything else is a no. Do we see that? Now we want to take the union of this set with C. So A intersect B union with C. If it's a union, you are in one set or the other or both. So as long as I see a yes somewhere, I'm okay. But this first region, no, no, it's not in one or the other or both. That's a no. No, yes, okay, that works. No, no, that's a no. Yes, no, yes, 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 no, yes, yes, no, yes. So the only places I'm going to have a no for an intersection is if it's not in either set. So 3 would be a no, 1 would be a no, and 8 would be a no. There's 1 is the no, there's 3 is the no, and there is 8 is the no. So I have successfully done the analysis for the region A intersect B union C. So which regions do I have? 2, there's region 2. 4, 5, 6, 4, 5, 6, and 7. So region 2, 4, 5, 6, 7, those are the ones I need to shade. So my goal is to indeed shade those regions when I draw my diagram. I'll put it together. What is that going to look like? There's 2, 4, 5, 6, and 7. So there's the shaded region for A intersect B. Here's A intersect B. These two regions are in both A and B. Or C. These 4 regions are C. So you might be able to think your way through that. But this analysis process is nice. It will make some of the more challenging problems doable. All right, the last one I want to do is I want to prove that the set A union B intersects C is the same as A union B intersect A union C. To do that, I'm going to construct Venn diagrams for both and show that they're the same. So we'll start with A union B intersects C. So same strategy. A, B, C, regions 1, 2, 3, 4, 5, 6, 7, 8. A is regions 1, 2, 4, and 5. There's the yeses. B is regions 2, 3, 5, and 6. 2, 3, 5, and 6. C is regions 4, 5, 6, and 7. So we're going to start with B intersects C. So where are B and C both true? For an intersection to be true, you've got to be in both sets simultaneously. B and C. Maybe you can look at the picture and see where B and C are both true. Looking at our yeses, where do we have two yeses? That would be region 5 and region 6. So region 5 and region 6 would give us B and C both being true. So looking at that, region 5 and region 6, B and C both true. All the rest are wrong. I want to take the union of that with A. So how are we going to do that? It's got to be in one or the other or both. So the only way the union fails is if it's no-no. So again, A union B and C. Do I have a no-no? A is yes, B intersects C is a no, so that's going to be a yes. A is a yes, B intersects C is a no, that's a yes. A is a no, B intersects C is a no. So is it in one or the other or both? No. Region 3 is a no. 4, A is a yes, B intersects C is a no, so that's a yes on union. A is a yes, B intersects C is a yes, it's in both, so that works as our union, as our OR rule. A is a no, but B intersects C is a yes, that works as a union. But our last two, 7 no-no, 8 no-no, so those are no's. So wherever I have no-nos, I lose the union, because it's not an either. So where are my no-nos? 3, 7, and 8. Notice 3, 7, and 8 are the no-nos, so that is not in the union. So to construct the Venn diagram, I will shade region 1, 2, 4, 5, and 6. 1, 2, 4, 5, and 6. So what is that going to look like when we shade those regions? 1, 2, 4, 5, and 6. Try to visualize it first. And here they are shaded. 1, 2, 4, 5, and 6. So that is our Venn diagram for A union B intersects C. Well, I want to use the Venn diagrams to prove that these two sets are equal. So next I'm going to do a Venn diagram to prove that A union B intersect A union C is the same Venn diagram. That's our hope. So here is our original regions, the sets, yes, wherever the regions are contained in that set again. A, region 1, 2, 4, and 5, 1, 2, 4, and 5 in A. B, 2, 3, 5, and 6, 2, 3, 5, and 6 for B. C, 4, 5, 6, 7. First I want to do A union B. Now A union B, is it in one or the other or both? Yes, no, that's a yes. Yes, yes is a yes. No, yes is a yes. Yes, no is a yes. Yes, yes is a yes. No, yes is a yes. So all of them are yeses until I get to the last two. No, 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 no. So region 7 and region 8, you can see those are outside A, outside B. So 7 and 8 will be our no's for A union B. Everything else are yeses. Now how about A union C? Where do I have A union C? The only time I'm going to say a no on a union is if they're both no's. Are they both no's, A union C? That's yes, no, so yes, yes. Here we go. Region 3 is a no-no. 4, yes, yes. 5, yes, yes. 6, no, yes. 7, no, yes. 8 is a no-no. So I only have a couple no-no regions that are going to give me a no on a union. Again, 3, A is no, C is no, so A union C is no. 8, A is no, C is no, so A union C is no. And finally, I take the intersection of these two sets. Now, the only way the intersection is true is if both of them are true. It's got to be in the first set and in the second set. Yes, yes, that's a yes. Yes, yes, that's a yes. Yes, no, no. Yes, yes, that's a yes. Yes, yes, that's a yes. Yes, yes, that's a yes. No, yes, that's a no. No, no, that's a no. Intersection, they must be in both sets. So we have quite a few of them. So which regions am I going to shade here? Looks like region 1, region 2, region 4, region 5, and region 6. That's what I need to shade. So what is that going to look like? And that should look familiar because that is exactly the same set of regions that we shaded for A union B intersects C. So this table for A union B intersect A union C was the same as this table that it went yes, yes, no, yes, 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 no, no. So we wound up shading the same regions. When that happens, what have we done? The Venn diagrams are identical. So if that's the case, we can conclude that the two sets are equal. And that will conclude this lesson.